Ladies and gentlemen, please welcome to the stage Vice President of Events and Industry Strategy, SME, producers of Rapid Plus TCT, Debbie Holton.
Good morning. Yeah. Welcome to the first day of Rapid Plus TCT 2018. You guys have been busy. Do you see all the things you've been doing? It's impressive and incredible how much industry advancement and innovation has taken place in just one short year. So here's the big question. What's next? You'll be the first to know because you'll have joined us here at Rapid Plus TCT. You're sitting on the front row of this industry and we'll see firsthand what's coming next for our industry. SME is dedicated to increasing the adoption and advancing the progress of additive manufacturing technology. We're privileged to work with leaders like today's keynote speaker, Mike Packer, who are driving forces in today's manufacturing industry. Mike is a valued SME member, and he's an officer of SME's board of directors, so we're happy he's here today. We celebrate our members who give generously of their time to create content and programs, define industry standards, encourage the next generation, and work to solve technical challenges. You can find out more about how you can get involved with SME and all the things that are happening in additive manufacturing by visiting sme.org/3D. So we hope you'll visit that. I'd also like to call your attention to our amazing set design. The amazing podium here on the side, and these hexagons were actually additively manufactured by Macy Consulting and Titan Robotics. Aren't they awesome? Let's give them a round of applause. Great. So if you want to get your phones out, right, or your devices, your iPads, whatever you've got, we have another poll for you. We did some polling yesterday. We're going to have an interactive session here. So if you open up the Rapid Plus TCT app, or if you go to slido.com and you can enter the code RAPID EVENT, You can get set up here to participate in our polling, and it's pretty fun to see what everybody's thinking. All right, so let's go to the poll. What is the biggest potential opportunity in additive manufacturing? What do you guys think? Is it printing body parts, manufacturing in outer space, the incredible advancement that's happening in metals, full-scale production, or maybe just good old rapid prototyping? What do you think? Let's look at our results. They're coming in. Awesome, full-scale production. All right, that's good. Keep voting. We're going to keep that open for a little while, but you can see people are very excited about full-scale production for additive manufacturing. So that's awesome. So here's another question. We're not going to poll on this one, but I'd like to know what you think. Just because I can 3D print a part, should I? And what's the best machine and material to use? How do I truly leverage the power of additive manufacturing? Are you waffling about these kind of decisions? Not really sure? Well, you're not alone. Manufacturers don't always have the in-house knowledge or expertise to really determine the best way or whether they even could or should additively manufacture parts. This wastes valuable time and resources on trial and error in the manufacturing process. So we're fortunate at SME to be working in partnership with industry expert Dr. Michael Greaves, who's the executive director of CAMID at the Florida Institute of Technology, to solve this important issue with SME's I-Team. Please watch this short video.
Can I make it? Should I make it? And then, what's the best machine, material, and process for my part? Answering these questions quickly and accurately will help you make better decisions, be more profitable, and maximize design for additive manufacturing. SME is proud to launch a new initiative, the User-Driven Independent Technical Evaluation of Additive Manufacturing, or I-Team. I-Team is a virtual repository of additive manufacturing machines and materials, plus the tools you'll need to evaluate additively manufactured parts. SME is creating I-Team working in collaboration with Dr. Michael Greaves, renowned expert at Florida Tech, General Motors, and other industry leaders in automotive, aerospace, and beyond. Together, I-Team is developing a new expert system that will greatly accelerate profitable additive manufacturing. Join us. Be a part of an exciting new community where you'll have the tools you need to evaluate your parts, maximize design for additive manufacturing, plus match up with the best machines and materials. The time to accelerate profitable and effective additive manufacturing is now.
Please welcome Dr. Michael Greaves.
So I'm Dr. Mike Greaves from the Florida Institute of Technology, more commonly called Florida Tech. And I'm a distinguished university professor and the executive director for our Center for Advanced Manufacturing and Innovative Design. And our center is located in wonderful Palm Bay, Florida. We get a lot of visitors during the winter, go figure. But Palm Bay and Florida Tech have recognized the importance of manufacturing. And we're basically working on creating infrastructure and capabilities in advanced manufacturing, but especially additive manufacturing. And so, but I have to admit that I am a native of the Detroit area, and in fact grew up in the city next to SME's headquarters. And so I've had a long relationship with SME, decades old. In fact, for those of you that are familiar with the concept of the digital twin, I created and developed that and first introduced it at an SME event back in 2002. Kind of wallowed for a while, but it's really caught on in terms of understanding how we can use information to do a better job in creating products and focusing on that kind of capability. So I'm delighted and privileged to be working with SME in terms of creating this new consortium, I-Team, which stands for the Independent Technical Evaluation of Additive Manufacturing. And so what we believe is that by working together in a collaborative method, we can basically advance the additive manufacturing area and accelerate that advancement over time. And in point of fact, what our focus is basically to have the individual participants be able to benefit as they work in collaboration. And so while you may have heard that there's no I in team, we've put the I back in team. And so we hope that that we will benefit the individual participants, the companies, the users, the machine producers, material producers, and the ecosystem that we're focused on developing. And so I'd like to kind of run you through what our mission is and kind of where we're at in terms of doing that. So the IT mission is the creation and operation of an analysis platform and dynamic repository of equipment, material, and capabilities to evaluate the can I make it and should I make it. So the technical and business issues that are going to drive additive manufacturing. We want to engage feedback from actual user experience to close the gap between theoretical, what people think is going to happen, and the actual performance. Because by closing that gap, only by closing that gap, will we be able to move this area forward and convince the executive suite that they ought to make the necessary investments to drive this capability. We believe that additive manufacturing is disruptive technology, and the characteristic of disruptive technologies are they look like they're not ready for prime time or only useful for a small aspect of product creation and things like that, but quickly they overcome the conventional ways of doing things. And so we believe that additive manufacturing is that capability. And then we want to influence and guide design for additive manufacturing, what we're calling DFAM, to advance the design and parts and assemblies to minimize material usage, complexity, and resource usage. So we think the big opportunities is not necessarily in the existing parts, although we think that there's opportunities in that particular area, but designing new parts that we couldn't design before that will be lighter, have less parts, and have capabilities built in that we can't build in with subtractive capabilities are going to drive this area much farther. And so the intent of iTeam is to build this ecosystem that will basically help accelerate because users are telling us that they need to have confidence in making recommendations to management about the can I and should I. And SME is in a very unique position to be able to be a trusted third party for these users to help make those decisions. We think that not only it benefits the users, but it will benefit the machine producers and material producers in shortening sales cycle times and having better informed a user community to make better decisions and to be able to be confident in the decisions that they make. And so the focus of what we're going to do is to build out a platform that will be this informational repository that will help drive the idea of additive manufacturing information. And so the platform is called the Rapid Additive Manufacturing Platform, RAMP, and the architecture looks like this. It's a layered architecture that basically will create this idea of a central repository of all the machines and materials and capabilities that will form the core of it. We're obviously very concerned about security, and so we have plans in terms of behind the firewall for those companies that are concerned about intellectual property, and then obviously the ability of having a little marketplace or ability of being able to add capabilities from users. So the top part is the thing that we're very excited about, is the ability of basically collecting all the information in a single place to basically be able to provide sort of a one-stop shopping for information and capability analysis in additive manufacturing. And so across the top you see that we sort of define areas that we think that the applications that can be built by not only the users themselves, but the providers, manufacturers, for basically doing the analysis of can I build it and should I build it is extremely important in being able to do that. And we've driven off this repository that we've created and I'll show you very shortly. We basically are looking at users having, free apps, for fee apps. We're going to collect the guides, guidelines, standards. We're not a creator of those things, but they all need to be in one place to have users have the capabilities of being able to do that. SME has an extensive library of material, educational material, and videos on additive manufacturing. We will collect those there and be able to provide those. At a sort of the top level is this thing that I have identified as SAM-CT, which is a methodology developed by General Motors, and then a proof of concept was financed by the United States Center for Automotive Research, and it stands for size, accuracy, and material, cost, and throughput. So that is the can I build it and should I build it? And so we actually have created an app, and you can, if you go to the SME booth, you'll be able to see it evaluate parts along those particular bases. And so U.S. Car has given to SME the rights to use this capability. So that's at the very high level, just to show you what's possible. We also have gotten Infosys, which is a major software or IT developer, and they have they're showing in our SME booth costing modules that will build into this platform. So this whole idea of basically being able to have all this information in one place and have a platform where we're able to accelerate the advancements of additive manufacturing by having users have confidence in the can I and should I decisions before they basically make decisions about making expensive acquisitions to their management. If they're not comfortable about doing that, it's not going to happen. So we need to accelerate that and to take advantage of the fact that it is a disruptive technology and we really need to advance it. So what we're releasing today is this iTeam repository inquiry, and this is the form that's out there that you can put in the criteria that you're looking for particular machines, and it will send you back the list of machines that meet those qualifications. We have it populated with the machines that are in use today and are actually being sold, and but this is a beta release of it. We are looking for the community. Again, this is a consortium of users and machine material producers to give us feedback, and if we're missing information on it, my Florida Tech folks are basically working to do that. And so we will have a process in place that allows us to update this on a constant basis. So I have grad students that are working to basically make sure that this information is correct. And so I would encourage you to give it a try. Maybe not all at once since it's a beta version, but I think that you'll be able to see that we are able to go out and search on particular capabilities. So this is a repository that forms the core, but what we want to do is to build upon that, these applications and analysis. And again, I'd encourage you to stop by the booth and look at the SAM-CT tool that was developed by us for the United States Center for Automotive Research. So how do you get to this form to give it a try? So if you go out to the SME iTeam site, which is sme.org/iTeam, you'll see there's a button that says to try the iTeam tool. And so go out to the website. You'll see the video that was shown before, and there's other information about iTeam. We'd encourage you to be part of iTeam. We had a user meeting yesterday and got very favorable results. But again, as a user-driven organization, we want to make sure that we're focused on the needs and issues of our constituency in order to be able to do the best job that we can in developing these capabilities. And so you have two nonprofits working on this, obviously SME and the Florida Institute of Technology. So we don't have a profit motive, but we do have a motive to get this right and to do a great job in terms of advancing the capability. You can send us information and contacts. We have an email, iteam@fit.edu, that will basically, we're looking for suggestions, ideas, tool issues, things that will help you make those decisions. And so with that, I thank you for your attention this morning. Go to this website and give a try of the tool, and certainly visit the pod that we have in the SME booth next door. And we look forward to getting feedback and moving this forward. We do have a development plan where we'll be adding things as we go along, and so our focus is to kick this off. So thank you very much for your attention, and have a great show.
Thank you, Dr. Greaves. We hope you'll stop by the SME booth, which is number 2339. It's actually directly behind the stage here, to learn a little bit more and help us to shape iTeam. We also have a really cool little promotion we're doing, so if you're waffling about whether to 3D print a part or not, you all got some coupons coming in here that send you to the SME booth. We have a waffle wagon. So if you come to the SME booth and you look at iTeam and sign up to get more information, you'll also receive a coupon for a waffle. So that's pretty exciting, all in 3D. So please join me in welcoming Sean Sullivan, Director of Materials and Surface Technology, to introduce our Conic suite of aluminum alloys for additive manufacturing. Please welcome Sean.
Good morning, and thank you, Debbie, for the kind introduction. I'd like to take a moment just to introduce my colleague, Dr. Lynn Carabin, who is leading all of our alloy development at our Conic and brings over 20 years of experience developing aluminum alloys for aerospace applications. We are both proud to be here today to introduce you to the innovations that our Conic is bringing to help shape the 3D printing world. This morning, we're going to introduce to you our first wave of new tailored aluminum alloys specific for additive manufacturing. But before we get started, for those of you wondering who our Conic is and why we're qualified to participate in the additive manufacturing marketplace, we're going to introduce you through a very short video. So as you can see from the video, our Conic brings a rich and deep legacy in materials and manufacturing expertise. We've been applying that expertise to additive manufacturing for over 2 decades, to everything from our tooling for our operations to more recently printing production parts for aerospace applications. On the screen behind me here, you can see an aerial shot of our Research and Development Center in Pittsburgh, Pennsylvania, which some in the audience may have gotten to visit last year at the Rapid Conference. What I'm really excited about now is in 2016, we opened our metal powder facility, and we have been placing our focus deeply into developing new novel alloys tailored specific for additive manufacturing. Combining that materials expertise along with our core comprehensive capabilities of product design, powder feedstock atomization, 3D printing technology, post-processing including heat treatment, heat treatment, machining, and also finishing, we are bringing together an end-to-end flow path to enable the opportunity for our customers to experience additive manufacturing and unlock the true value of additive manufacturing. 3D printing is on the rise and our customers want the technology. But metal additive printing is still very complex. Today you can't just go and buy a printer, input metal powder, and press print and expect a high-quality part to come out of that printer. It's going to require deep expertise in product design, manufacturing, and materials to really make additive printing be disruptive as everybody is hoping it will be. And when we think about materials, largely today, the materials haven't been developed for 3D printing. We're replacing and substituting conventional metal alloys when really what customers desire is higher performance. An example of this is in conventional alloys for aluminum. Aluminum alloys have proven very difficult to print in additive manufacturing. They're prone to cracking, they require microstructural control, and they haven't yielded the material properties needed to produce high-quality parts. Aluminum, for Arconic, we see great potential in additive manufacturing. Everything from aerospace applications to automotive to industrial products and beyond. And for these markets, properties such as strength and density, especially in demanding applications where high temperature is required, is absolutely critical to the customer. And just as Arconic invented the aluminum industry over 100 years ago, today we are reinventing the aluminum industry for additive manufacturing. This morning, you're going to get to see not only our ability to print conventional aluminum alloys, but also new tailored alloys specific for additive manufacturing that expand the property capabilities to those never achieved before. We bring enhanced properties and enhanced performance to the customer for the first time. Lynn, let's introduce our new alloys.
Thank you, Sean. Arconic has developed two thermally stable aluminum alloys specifically for additive manufacturing. Both of these alloys require the rapid solidification rates associated with laser powder bed processing and cannot be made by conventional ingot metallurgy methods. In fact, by leveraging the rapid solidification rates, it enables us to introduce alloying additions that really help us expand the performance envelope, especially at elevated temperatures. Our approach has been to balance performance, printability, and cost. Ultimately, this gives our customers the ability to choose the alloy that best meets their needs. We've compared our materials not only to the industry incumbent aluminum 10 silicon mag, but also to the conventional 2000 series aluminum alloys, as these are the ones that are typically chosen when aluminum is expected to operate at elevated temperatures. We see our highest performance alloy to develop twice the elevated temperature strength at 200 degrees C and beyond as compared to the conventional 2000 series alloys. The alloy also provides an order of magnitude improvement in elevated temperature fatigue life at 200 degrees C compared to the aluminum 10 silicon mag alloy. And of course, at elevated temperatures, creep resistance is also important. Creep, of course, is the material's deformation and eventual rupture when subjected to high stresses at elevated temperatures. Our highest performing alloy actually exhibits more than 4 times greater creep rupture lives than the conventional 2000 series alloys. The alloy is also suitable for room temperature applications for structural components due to its 85% higher strength at room temperature compared to aluminum 10 silicon mag. Now, when complex geometries are critical, one can choose our ET389. That alloy has exceptional printability and also delivers elevated temperature performance and thermal stability. Both alloys can be printed at 30% faster speeds than typically used for aluminum 10 silicon mag. So, in addition to these two alloys for elevated temperature applications, Arconic is also developing AM versions of traditional wrought alloys. As Sean previously mentioned, the 2000, 6000, and 7000 series aluminum alloys are historically prone to solidification cracking issues. What you see here is that Arconic has developed its own version of AM version of 6061. We've shown with that alloy that we can build complex 3D parts and show that they are crack-free. In addition, we meet the tensile properties of conventional wrought 6061 T6. Furthermore, we've demonstrated that we can take the ideas we used to develop this AM6061 and apply that to the 2000 and 7000 series alloys, also making them crack-free and printable. So we're doing this by optimizing our materials, optimizing the additive manufacturing processing in order to create the desired microstructure. On the slide behind me, you can see that we've created a comparable microstructure in our AM6061 to that which we see in our 6061 T6 forgings. So, as a materials leader with 130 years of experience, Arconic is building a bridge to future AM applications. We're taking our alloy development expertise, our knowledge of microstructure, and optimization of AM processing in order to deliver targeted properties in AM parts. And again, we do this by using the rapid solidification to expand the property envelope, and at the same time, we're also making our own AM versions of the conventional wrought alloys.
So as I hope you can see from what Lynn just shared today, Arconic is introducing 3 new alloys to the AM marketplace that are really delivering on higher performance and making those conventional alloys that have been truly difficult to print in the additive world now printable. Arconic works with a number of different equipment suppliers when we're doing material development and in our additive manufacturing footprint. But for these aluminum alloys, we have developed all of these on EOS state-of-the-art equipment and developed the print recipes to go with them. Arconic and EOS are collaborating to make these materials available to our customers through a customer pilot program, and Arconic is committed to deliver state-of-the-art laser powder bed solutions all the way through manufacturing scale-up to get to full production. So in summary today, what I hope I leave you with is Arconic is reinventing the aluminum industry for additive manufacturing, bringing better printability, better properties, and enabling better products for our customer. We're eager to talk with you and invite all of you in the audience today to visit us at booth 1818 and to talk with Kevin Crehan or Pete Emmons on how you can become a part of our customer pilot program going forward. We thank you all for your attention this morning and appreciate the time that we've had to introduce these alloys. Now, without further ado, I also have the unique pleasure today to introduce today's keynote speaker, Mr. Mike Packer, Director of Manufacturing from Lockheed Skunk Works. Mike comes to us this morning with over 40 years of experience in production engineering and operations, and Mike is proud to have led the X-35 flight demonstrator for Lockheed Martin, which now has reached full-scale production right here in Fort Worth, Texas. Arconic is proud to have partnered with Lockheed to develop metal 3D printed parts that are on NASA's Orion spacecraft. And I, like many of you, am now eager to hear Mike and Lockheed's perspective on how additive manufacturing is going to continue to shape our future. At this time, we'll have a short video from Lockheed Martin. Thank you all.
Good morning. Hopefully that got everybody going a little bit. Why show the flight test completion for F-35 at the Additive Manufacturing Rapid plus TCT conference to get it going? First of all, jet fighters are always exciting, get the blood moving, get people up and going. Always exciting. And it produces the sound of freedom. Secondly, recognition in this case for an enormous, monumental, historic achievement of an enormous enterprise team. Includes primary partners, Alcoa, obviously, Pratt & Whitney, Northrop Grumman, BAE Systems, 1,500 suppliers in 46 states, 15 countries, 195,000 people involved in bringing this to reality. Third point, why show it at Rapid? Additive manufacturing was a tremendous enabler for bringing this to reality. And I'll talk a little bit more about those enabling applications of additive manufacturing. And then finally, really the reality for aerospace and defense of additive manufacturing, it is an enabler. Our customer doesn't buy the additive. It's a process that allows us improvements of affordability, cycle times, and quality. Part count reduction that allows all of that to occur. So it is an enabler. That isn't to say that there aren't products that are additive. Certainly medical devices, prosthetics, those kinds of things. On down to arts, dresses, kind of living wear that is additively produced. Some of the vehicles, major bodies, those are purchased by the customers. But our customer is buying a weapon system. And all of the enablers that feed into that allow us to produce those in an affordable, quick response time. 9 years, 10 months to the day seems like a long time. Think about it this way for that flight test completion. 3 different aircrafts, 3 sets of requirements for multiple customers, 3 primary customers in the US, and then allies around the world. 3 airplanes were qualified to initial operational capability. All of the system development and demonstration was completed 9 years, 10 months to the day. Graham G.T. Tomlinson flying the first June 11th, 2008. Whizzer Wilson flying the last CV or carrier variant aircraft, April 11th. So it was a very recent accomplishment. So, into an OEM's perspective of additive. A little bit, just a couple of slides on the overview of Lockheed Martin. We're obviously not a small and medium enterprise. Very large enterprise, 100,000 people worldwide. Half of those are scientists, engineers, researchers. We're in 400 facilities globally, operating in over 50 countries. And those global international employees, over 7,000 employees. Business structure. I'm actually part of the aeronautics business unit, there to your right, but you can see the 4 basic structures of the business. Aeronautics, which is primarily, as you can see, with the product platforms, primarily centered around flying systems. Missiles and fire control, as it says, tactical missiles, fire control systems, both ground launched as well as air-launched. Also vehicle systems and fire control for those vehicle systems. Rotary and mission systems is a combination of the Sikorsky acquisition along with the mission training systems folks. So you can see, obviously, rotary aircraft, but also test systems, electronic and radar systems that are shipborne, and training systems. And then finally, space. Sean mentioned Arconic support of some of the space systems. We have over 100 production parts on the Orion program that were additively manufactured. And their primary business, spacecraft and launch vehicles. Additive capabilities at Lockheed Martin. You can see small polymers, a lot of fused deposition stereolithography goes back to the mid-90s when we were introducing these. We've introduced more additional technologies. Some of those were actually flying parts. Skunk Works, we have the advantage of low flight hour. They're not 9,000 hour requirements like an F-35. They're low flight hour, concept demonstrator, prototype, one-off, two-off kinds of programs. So we don't have some of the durability and life constraints with some of the parts. So we've had production flying parts for years. A good example, inlets that are serpentine, very complex geometry with baffles in the inlets. Couldn't be produced any other way but additively. Large polymers, we have expanded to larger and larger. A lot of these were applied for tools at this point in time. Small to medium metals. Electron beam, we've continued to scale up. I'm going to show you a little bit more as an example of what we're doing in electron beam because it's the larger structure that is really the grail for us, where we can eliminate a lot of parts and tremendously accelerate the velocity of part production. And then advanced materials, or designer materials, if you will, designed and specifically tailored to maximize the leverage of additive manufacturing. Current philosophy started with tooling. A lot of, particularly FDM, a lot of FDM tooling, various polymers with those various tools. They range from very small locating tools to large drill plates, to simulations of payloads for weapon bays, for gear bays, for satellite structure. You put those payloads, you can very rapidly put together a simulated mass of that with the dimensional characteristics and features to look at where there could be interferences or installation challenges with that particular piece of hardware for the real hardware. Support equipment. On the tools, just to give you a scale, about 5,000 tools at this point in time. Back to F-35, about 4,000 of them for F-35. C-130, C-5, P-8, P-3, a lot of tools have been built for those. We envision over the next 5 years a forecast of about 12,000 tools will be built using additive processes, and most of those are polymers. We use them for forms for composite fabricated parts. Non-critical applications and support equipment, we've got hundreds and hundreds of support equipment that's been produced. The next ones that we see in terms of the continuum of application is really going into spares. And we see some of those low volume production parts with some of the complex weldments, again, to Orion and some of the spacecraft articles. Secondary structure, some of the locating structure, tertiary in terms of its loads, heat exchangers, ducts, those kinds of parts we are producing today. Primary structure, as I mentioned earlier, is the Holy Grail. That's what we see, growing a torque box. That torque box won't look like a torque box of a normal wing torque box. It did in the past if we optimize it for the load paths and what the additive capabilities provide us. But that is the Holy Grail, and there are a lot of challenges and still a lot of work ahead of us to go and achieve that. Some of those deployed parts you can see here, and these are in terms of production parts. You can see, again, back to spacecraft, a number of spacecraft parts. As I mentioned earlier, the polymer tools, and then fiber placement as a process in and of itself. Let me talk a little bit about the electron beam direct manufacturing qualification example for F-35, because this is where we're really trying to shake out and shake down the basic sets of processes, the rules, the constraints that we have in order to realize a qualifiable part with all of the design guides in place and all of the allowables for the material in place so that we can achieve that qualification. The process itself, for those that aren't familiar with it, weld wire that is very specifically tailored and crafted for this process with very high deposition rates. using closed loop control. So it's essentially a weldment. Think of it as a weldment. You can see the process flow to your right, where we do all of the NC path programming for that part, where it actually lays the metal down, the wire down, and fuses that weldment. The net part shape continues to grow by going through those NC paths. It's then machined to a final finish shape. You can see, as I mentioned earlier, with the closed loop control on the right, on the lower left column of the right-hand side of photos, the closed loop versus the manual controls, a lot more control of what that net shape is for a lot higher yield of the material itself. And then you can see the notional part there. Applications that are potential for F-35 and under consideration, you can see range from pretty straightforward spars and ribs to a flapper-on spar. Flapper-on spar, 10 feet long. You can see basically a foot by 10 feet. So it gives us a good challenge in terms of laying that, and the geometries tests a lot of the process controls to achieve it. Qualification, as I mentioned, that is the challenge. That is the challenge ahead of us. And as Michael spoke earlier, I-Team is going to lead us down the path with starting to build more and more robust databases that will feed some of these qualification implications and some of those requirements to achieve qualification. But there are very specific focused efforts that have to take place as well. And you can see surrounding the F-35 qualification what those are in terms of basic commercialization of the process, to scale it up, commercialize it to robust industrial standards and not lab standards, to take the whole supply chain and integrate that value stream of all of the processes that occur with process control checks at each step of the way. We have IRADs and contracted research in terms of some of the inspection methodologies, development of the allowables, and then continuing on with small business innovation research in the commercialization and the process development cycles. Design allowable development, you can see the test matrix, you can see some of the parts, a huge effort in terms of defining what those design allowables are. Once again, there's a connection with what I-Team is doing and collecting various data from the metallic additive manufacturing. Small Business Innovation Research Program for commercialization and development of the closed loop cycle, the closed loop controls activity, to constantly measure, feed that back in, make adjustments to the machine and the process as it's building and growing that part. Supply chain, small business innovation research, and a mentor-protege project that lays out that whole value stream in each step of the way. How are we setting up inspection criteria and process progress criteria in the realization of the part? NDI, a particularly difficult challenge. We have a contracted research and development program in terms of inspecting the part. You can see the banded structure there in the photograph, and one of the challenges that this creates with the columnar structures of the grains themselves is the inspectability. It's inhibited by that grain structure. So we have to overcome what that structure is with additional or different inspection technologies to achieve, are there any flaws, whether they're inclusions or any kinds of gaps or any kinds of defects within the actual weldment. And it also has an impact on the fatigue performance of the part itself. Primary structure, in order to achieve that, we've got to overcome that. Current status, basically on hold until the risk reduction and each of these CRADs and IRADs are accomplished. The SBIRs are completed, and we actually move into phase 3 of the SBIRs into commercialization and deployment of those processes with inspection techniques that we can verify we have exactly what we expected, what we designed for, and what we need in terms of requirements for the product. Full needs, you can see, engineering and materials development. I mentioned designer materials before, special crafted, whether it's metallic, crafting the alloys to leverage the additive process and to address some of the grain issues that we see with the current materials. On the polymer side, specially crafted and designer materials to achieve higher performance, longer life. The tools have a specific life to them. We can rapidly produce them at very low cost, so it's not a barrier in any real sense, but the more life that we can get out of those, obviously, it still continually drives that cost down. There are also designer materials that we envision and we're doing already work on in terms of some of the product platforms and the enabling technologies that involves additive at the Skunk Works is actually building in provisions and utilities into the actual parts and skins themselves. So not having necessarily conventional wires and tubes, but actually use the structure and the skins of the structure to provide the provisioning for utility distribution, for power distribution, for actually reconfiguring while a particular product is in performance. If it's launched out of the water, it's going to be in one configuration. As soon as it hits atmosphere, it'll reconfigure itself from a shape standpoint. Those are some of the visions that we have that can be enabled through additive manufacturing. Repeatable manufacturing process certification is just a mandatory. It's an imperative in order to really deploy, obviously. And then cost and span analysis versus conventional. Michael talked directly to that with the I-team, and we're involved with the I-team and feeding that in so that we can not only produce and extract the data, assimilate the data, analyze that data, but develop tools to be able to sift through, filter, and start to automatically make the decisions on which path to go and which configuration to deploy. And then finally, operational digital transformation. It changes the way we operate, and we have to address that from a systems and a people standpoint. It strongly aligns with overall future capabilities that center around that digital transformation. All of the security, the Internet of Things, tying machines together, taking the common data right out of the system, additively or directly manufacturing that part. You can check it against that CAD database automatically. Intelligent systems and machines that can address the kinds of closed-loop feedback and make the adjustments necessary to maintain those controls. And then design it anywhere, build it anywhere. We see some of that with firms like Local Motors, where distributed factories, distributed design of the parts that go into those factories, stand them up and sunset them very rapidly based on where the product is needed. So it allows us that design anywhere, build anywhere capability. And then finally, performance metrics and analytics, kind of the bots or the robots of the data. Pull the data in, analyze it, present it in a fashion that is very quickly assimilated and responded to. Where does it go to that next step? I mentioned a little bit about how much more we can leverage. This is an actual part that was a part detail on one of the radar systems, one of the spacecraft systems at Space Systems in Denver. And you can see the evolution as they got into it. It basically was, okay, we can do an additively manufactured part or fabricate it directly from the database, but it looks just like the conventional one there on your left. Well, why do that? We've already got the processes in place for the subtractive. We're not really achieving anything other than we're verifying, yeah, we can build it directly. Now, we've gotten more mass property efficiency as you move from the left to the right, more and more mass property efficiency until you can see all the way at the far right a product that meets the need of this particular part detail, but it sheds all of the mass property that is unnecessary for it, because now you have an ability to just grow that part based around what the load paths are, what kind of stiffness you need, what kind of fatigue properties, life that you need, thermal properties of the part itself. all of that can be put into the design rules, and you only add what you need, as opposed to producing or machining away all that you don't need. And you can see the part on the right, producing that subtractively would be very costly. Summary, we've invested and continue to invest heavily because we do see performance and design excellence and product excellence in the future with huge payoffs in terms of lead time and cost to fabricate. We start with production fixtures. We're very pervasive with the fixtures, the jigs, the tooling, the support equipment. We're now introducing spares that are battle theater spares, where you've got an interim spare until a qualified part can be provided so that the weapon system itself can continue to operate in theater. And so those spares are going to be a good building block learning lessons program for us to continue to shake down the processes. And then ultimately the potential aerospace, underwater, ground vehicles across the board. But we've got to overcome the maturation, as you can see down below, which really centers on qualification and all of those processes that revolve around that qualification. And then finally, the design rules and tools to really teach the students how do you design something for an additive purpose, as opposed to design it and then trade off. Should I do it subtractively or additively? Yeah, and there are going to be some of those kinds of choices made, but if the parts are designed at the onset from an additive maximum leverage standpoint, then that's going to reduce the cycle time of bringing those ideas to reality. And now, Richard, if you can tee up the Mantech video, I wanted to give you, this is about a 5-minute, almost a 6-minute video of the broader manufacturing technology activities and investments at Lockheed, of which obviously additive manufacturing is one of the key parts, but it gives you a broader perspective of what we're doing, what our primary partners, Northrop Grumman, BAE Systems, Pratt & Whitney across the enterprise are doing, and how Alcoa is supporting, Arconic is supporting us in that. Richard?
F-35 production is constantly searching for ways to reduce cost and improve quality for the F-35. Affordability is a priority for us, and manufacturing technology is just one way to build the newest 5th-generation fighter and bring the F-35 cost down to a 4th-generation price.
Lockheed Martin is developing manufacturing technologies to solve the problems we have in production. And not only to just develop those technologies, but to take those technologies, develop to the point where they can hand us the keys and we can implement it on production.
Forget the programs F-35, C-130, F-16. This is more about an internal Lockheed Martin investment, providing values in the manufacturing technology arena across all current platforms, while it's uniquely positioning ourselves for 6th-gen platforms and beyond.
Lockheed Martin is not only developing additive manufacturing, but Lockheed Martin is using additive manufacturing to produce tools for the F-35 program. We have produced more than 5,000 tools already from systems like MakerBot and Stratasys, and also use the technology to solve floor problems by using rapid prototyping techniques to make tools for the mechanics. In addition, Lockheed Martin is working with innovative companies such as Siaki to use titanium wire and electron beam welding to actually grow bulkheads for primary aircraft structure. The industry has been working on ways to machine titanium better, faster, cheaper forever. And one of the companies we work with came up with the concept of using liquid nitrogen applied right at the cutting tip. So by applying liquid nitrogen to cutting tip, cooling that cutter, not only can we machine faster, but we cool down the cutter and improve cutter life by a factor of 10. And by the way, liquid nitrogen is great, right? It's very clean. Once I cut the part, it's clean chips that come off the part. You don't have any waste treatment to deal with a flood cooling kind of device. So it's not only faster, cheaper, but it's very green. And those are all reasons that we're interested. So what Halo does is we put a magnetic device into the hole and underneath. And then when I put the other skin on top of it, the Halo device helps to, using that magnetic field, centers that hole, and I'm allowed to drill that hole straight all the way through that new part and into the substructure without having to do a lot of repairs on the airplane.
Digital thread in action on the shop floor is probably the most easily identifiable if that's the case. We take the latest version of the CAD model itself in 3D, download it to the projector itself, project it where the data is needed, when it's needed, onto the part, so that effectivity type version is updated at a flip of a switch. In this case, we are projecting fastener hole data. We can project work instructions. The technician's hands are free. They can actually just read whatever information that they need while doing their work, as opposed to holding a drawing with one hand while they do work with the other. In CFF, or the Component Finishes Facility, and AFF, the Aircraft Finishes Facility, these are very large 8 and 9 axis robots that coat the airplane. This particular material that we're spraying is unique to F-35, is our ability to hold extremely tight tolerances and contours over the entire OML of the airplane. There is a change in thickness very discreetly per the design of the airplane that is applied. We've developed essentially a robotic freehand to be able to spray thicker areas tapering to thinner areas, accurate and repeatable without any tooling.
Non-contact metrology, or the use of structured light, this technology is game-changing for us. Imagine being able to walk up to an airplane and take a picture of it, be able to extract that and put it back into the as-design role in CATIA. By doing that, we see exactly where the as-built is with respect to where it's supposed to be very quickly, and can tell when things are out of sync. We're going to be able to validate the airplane early in front. We'll take out millions of dollars in costs by things not going downstream.
The SALSA, structured light sanding aid, is used in conjunction with white light technology. What the SALSA enables us to do is the ability to take the data that came from the white light scan and take the differences between the white light scan and the original drawing, and then project that as a topographical color code. Thick places are red, so we essentially sand the red. And so we want to end up saying that everything is green or in tolerance. And so it's an interactive thing, if you will, between the physical world and the 3D data.
What excites me about manufacturing technology in the future is I see innovations everywhere out there, in books and magazines, on television. It's manufacturing technology's responsibility and purpose to take those innovations and bring them to Lockheed Martin.
Thanks, Mike. That was a great session. Let's give Mike a round of applause for all that great knowledge. So now we have the opportunity to, pick his brain a little bit. We're going to do some questions. Within the Slido app that you've been using to do the polling, there's a tab that says questions. So you can send your questions right up here, and they will be on this handy-dandy iPad. And we'll get your questions answered. We've got a few minutes to kind of go over some things. And I have a question first, though, Mike, before these start coming in feverishly. Tell me a little bit about, as additive manufacturing and all these new technologies are adopted within Lockheed Martin, what kind of culture have you had to foster? How do you really get the entire team to get on board with that?
Well, one of the aspects of the demographics of the aerospace industry, which goes through peaks and valleys, and the demographics with the early career people coming in now, we have quite a population in the late 40s to late 50s, and we've got quite a population in the early 20s to the mid 30s. And so with these incoming talent that comes in, one of the things we do is we do a lot of reverse mentoring. We obviously do conventional mentoring as to this is what the business is about and how we run the business and what the products entail in order to realize the ideas of creative engineers. But reverse mentoring allows us to share more broadly what the tools and the techniques are really to bring those things to reality. Diversity, as we've talked in the past, is an enormous pillar of value to Lockheed Martin as a whole, from our CEO, President, and Chairman, Marilyn Hewson, all the way down through the organization. It is diversity of ideas, talent, people, background, expertise, and all of that coming to bear in a very open, candid discussion environment. And that allows us really to continue to invite these new. Skunk Works, as one of the microcosms within Lockheed Martin as a whole, we have a distinct advantage of that's the way the Skunk Works always has thought, always thinks, and the way we operate today and will in the future is very, very small, diverse teams that are focused on the creation and ideation of a product and the realization of that product, tapping into the skills of each and every one of the individual contributors.
That's fantastic. The questions are starting to come in, so thank you. I have a question here from Mark. What AM materials do you recommend for future aerospace designs? So what do you see coming in the future?
Well, again, still the pretty conventional, and some of the advancements in the polymers for the tools are very valuable because of the low cost and the ability to very quickly fabricate those tools, prototype parts for design ideas, so we can go through several rapid prototyping cycles of if we need to add a part or make a part or change a part, what those various alternatives, analysis of those various alternatives are based on real empirical rapid prototyping. So we see the polymers there. We see continued growth of the metallics in the secondary and tertiary structure. And as I mentioned, the real holy grail from a span time and to really maximize the leverage of direct manufacturing is really primary structure. And we see titanium, superalloys, the Inconel families, as well as aluminum.
Mm-hmm. That's great. Here's another question too. Someone's really got big ideas, okay? So do you ever envision printing a plane decades in the future?
We actually had a president of aeronautics that he actually stated that as an objective in the mid-90s. And we built a laboratory. It was called Lightspeed at the time. Some of the very early laser sintering processes to actually grow an airframe. It obviously, growing the whole plane, it depends on the perspective of which OEM you're talking to. If it's the engine guys, the airframe is something to keep that propulsion system clean and dry. If it's the mission systems people, it's to keep their boxes dry and working. If it's the airframe, propulsion and mission systems are things we put in it. But from an airframe standpoint, that was his vision now, almost 20 years ago, is growing a plane. We see Jay Rogers doing some of that with automobiles. There's obviously a lot of different load conditions and performance characteristics that complicate that for aircraft, but that still is, I think, a visionary objective that we want to continue to pursue, and what comes along the way is going to be value added.
That's great. Some more questions. Thank you very much. Keep those coming. How well is this technology, additive manufacturing, flowing down through your supply chain?
Extensively, and as I showed, we're doing small business innovation research to commercialize it, because we are in the business of ideating, creating, integrating weapon systems at the full system level. The fabrication of the details and the parts that go into it, We obtain the vast majority, 2/3 to 3/4, depending on the product, of that through our supply partners. And so it's already pretty extensive down there. We see in America Makes and other venues where we can share what those needs are and what their developments are and the developments that we're doing from an independent research standpoint and how those can converge to add value to the entire supply chain as a whole.
Great. Here's a question from Bo, thank you. It says, you mentioned shape reconfigurative parts in your presentation. So is Lockheed Martin looking at the potential of 4D printing too, shape memory materials and those kinds of things?
Good question, good idea.
Right?
We will now.
Thanks. See, we're all working together. It's fantastic. Here's one from Kelsey. What are some of the biggest challenges you face in implementing additive manufacturing into your products? And it says also in items sold to the government. So I assume you're talking about maybe some regulations or
Right.
defense acquisition regulations, those kinds of things.
It really is the qualification of the primary structure. Where it's secondary structure and lightly loaded parts, pretty straightforward. We have enough of an understanding of the design allowables to have margin in those parts for those lighter loaded parts. For primary structure, the margins would become prohibitive, and it would overcome the value added of direct manufacturing processes. So it really is going down that path of qualification, inspectability, material allowables, design rules, design margins, and there's going to be hundreds of thousands of coupons and test parts that'll have to be produced to establish that. As many know in the aerospace industry, you know, how long have we been working with composites, carbon-based composites, and we're still kind of going through. And those that work with the Navy, weldments as a whole, which is an aspect of additive manufacturing or a dimension of it, the margins become prohibitive for welded structure. And so that's really going to be what we have to overcome, is the whole qualification process that's going to take the entire industry, the I-teams, and all of the various institutes and venues that are working these kinds of problems to bring it to reality.
That's great. There's a couple questions here I'm going to kind of combine, having to do with like fatigue testing and tolerances and those kinds of things. So I guess that kind of figures into the whole idea of part qualification.
Right.
You talked a little bit about your non-destructive inspection and testing.
Right.
So what are some of the maybe the key factors in the testing that you guys are looking for when you've got the additively manufactured parts?
Well, clearly it's going to be what those allowables are that drives the kinds of margins that you see, what those fatigue tests are, and any kinds of inclusions or porosity within the part detail that would affect the fatigue and the strength and the durability of those parts, the life. So all of that becomes part of the qualification program.
Okay, so our last question for now, and then Mike will be around afterwards if you guys have some questions you'd like to ask him in person. What does the future hold for additive manufacturing at Lockheed Martin?
Oh, I think it continues to accelerate the speed with which we can turn ideas into reality and introduce products that meet what the customers require. It allows us to accelerate supporting the warfighters that are in the field with either damage from battle damage or just damage to piece parts and some of the weapon systems that we can very quickly respond and replace on site. We can have a trailer with additive equipment there, produce the part, and put them back into a safe condition and what that weapon system was doing to protect them and achieve the missions.
Awesome. Thanks, Mike. Thanks very much
Okay.
for a great session.
Thanks, Debbie.
Thank you.